In this video, we solve problem 13 from section 8.4 of the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. This is from the trigonometric substitution text section of our text. Now, at this point in the textbook and in the course, we look at this and we say, do I have a basic rule for that? And we don't. If there was no 2 there, if that was just 4 over x squared plus 4, I would have a rule for that. That would be an arctan antiderivative, because we know that 1 over the expression x squared plus a squared, we know that the integral of that turns out to be 1 over a times the arctangent of x over a plus c. So if there was no 2 there, I would factor out that 4, and I would say 4 squared is our a squared, so a was equal to 2, and we would get an arctan. But unfortunately, there's an exponent of 2 there, so that won't work. Now, since there is an exponent of 2 there, we might also be tempted to use a u substitution because we've got this expression inside the parentheses, but the derivative of that expression is a 2x, and there's no x up there. So the u sub is not going to work. So it's not an arctangent, but it looks like an arctangent, and it's not a u sub because the x that we need is not there. So we're going to have to do something else. In that case, we're going to use a trigonometric substitution. If it looks like an arctan because it has an a squared plus x squared in it, but it's not an arctan and it's not a u sub, we're going to make a tangent substitution. So let's write that down. Since the integrand involves a squared plus x squared, or x squared plus a squared, same thing. We can add in any order we want, right? We're going to make a tangent substitution. And that is x equals a times tangent of theta. Okay, so consistent with that, we're going to start by preparing to substitute. In order to prepare to substitute, we identify a, we define define x. And once we've defined x, we compute dx, and then we simplify this x squared plus a squared. You don't have to simplify first, but I find the computation is much easier if you do that simplification ahead of substituting. Okay, that's the plan. So we identify a squared is 4. A is the positive square root of a squared, so a is just 2. Now I notice that this is in a different order than this, but remember this x is our variable. So this x is a variable as well. The a squared is the 4, it's not the x squared. Okay, so a squared is 4, so a equals 2, and then x will be a times tangent of theta because our integrand involved an x squared plus a squared. Then you compute dx. The derivative of 2 times tangent of theta is 2 times secant squared theta d theta. And then we will simplify that x squared plus 4. Now x was 2 tan theta, so I'm going to replace this x with the 2 tan theta that I just defined right there for my x. Now I've got a product and I'm squaring it, so I square the 2 and I square the tangent. So I have 4 times tangent squared theta there, plus 4. And then I look at these 2 terms and I see that they have a 4 in common, so I factor that out. And then I look at what's left and I say tangent squared plus 1 is actually secant squared. I've got a Pythagorean identity that tells me that that's true. Okay, so we've done all of this. We're prepared to substitute. Now let's actually substitute, simplify, and compute that antiderivative. And remember what you're doing. You're making literal replacements. That 4 is still there. In the denominator, I'm going to replace the x squared plus 4 with something. So I'll just open some parentheses and leave a space for what I will replace it with. We're going to take that something and we're going to square it. And then we'll multiply by the dx. Now, x squared plus 4 turned out to be equal to 4 secant squared theta. So I'm substituting that in right here. Instead of writing x squared plus 4, I'm writing that. Now my dx is this over here. It's 2 secant squared theta d theta. So we're done with substituting. Now we just need to simplify. 4 times 2 is 8. And we can think of that as a fraction. That's going to leave us with a secant squared in the numerator. And the denominator, we've got this product squared. So you square the first factor and you square the second factor. 4 squared is 16. Secant squared is an application of this property from algebra. If you take a power and raise it to a power, you multiply those exponents. So I'm going to multiply the 2 and the 2 to get a secant to the 4th. So I've actually got 4 secants multiplying each other in that denominator. And that d theta is still there. Okay, and now we simplify. Got 2 secants up there, 4 down there. 2 of them will reduce, and that's going to leave me with a secant squared in the denominator. 8 over 16 is 1/2. I will factor that out. And remember from trig that 1 over secant is cosine. And if I square that, I can square that. So this 1 over secant squared that's left is actually cosine squared. And don't use the power rule here. We don't actually have a rule for this. But if we go to our trig integrals guidelines, we remember what they say. They say if the power of cosine and sine, the powers of cosine and sine are all positive and even, then we use our power reducing formulas to rewrite those even powers of cosine and sine in terms of cosine. So we've got this fact that we use. Cosine squared of some angle turns out to be equal to 1/2 of 1 plus cosine of twice the angle. I don't have an antidifferentiation rule for that, but I do have a rule for each of these terms. And of course, the 1/2 is just an extra factor. So we can replace this cosine squared of theta with 1/2 of 1 plus cosine of 2 theta. We can sub that in right here. That 1/2 times that 1/2 is a 1/4. And then we say to ourselves, do we have a rule for that? And a rule for that, we certainly do. The antiderivative of 1 with respect to theta is theta. The antiderivative of cosine is sine. If that was just a theta, I would be done. It'd be sine of theta. But since that's a 2 theta, if I've got a constant multiplying my variable, I have to divide by that constant when I compute the antiderivative. Distribute the 1/4 if you prefer. I prefer to. You don't have to. 1/4 times the 1/2 is going to give me a 1/8. Not their antiderivative in terms of theta, but I know for me as a student, if I'm working out this problem, I might be a little bit concerned about that 2 theta. With every other problem that we've worked, the answers were in terms of theta. So I'd have sine theta, cosine theta, tangent theta, that's fine. And because of that, we're able to use our triangle to write the answer in terms of x when we're done. But we can't do that with cosine of 2 theta or sine of 2 theta, not as it stands. But there is a double angle formula for sine. And it says this: sine of 2 times some angle turned out to be 2 times sine of the angle times cosine of the angle. So this is actually 2 times sine of theta times cosine of theta. And that I can work with, that I can use with the triangle that we're about to construct to write the answer in terms of x. So I'll substitute using that. 2 times 1/8 is 2/8 or 1/4. So this is my answer in terms of theta, but we don't want an answer in terms of theta. We want an answer in terms of x. So we need to draw that triangle. And we'll use our original substitution to label the sides of the triangle. Excuse me. We had x equals 2 times tan theta. Solving for tan theta, we get tan of theta equals x divided by 2. tangent is opposite over adjacent. Remember, so ka toa, toa right there. So that means if I draw my right triangle like this, if that's theta, the side opposite theta should be labeled x, when the adjacent side should be labeled 2. And then if we use the Pythagorean identity, or excuse me, the Pythagorean theorem, this squared plus this squared equals this squared, we can find that the hypotenuse involves that square root, or is equal to that square root of x squared plus 4. Okay, so we've got this triangle with the labeled sides. Now we need to use this triangle to write this answer in terms of x. Now our answer involves sine of theta, cosine of theta, and a theta, so we need to find all of those. Now finding theta isn't too bad. You just take the inverse tangent or arctangent of both sides. So if you take the arctan of the tangent of theta, you get theta. And then on the right, you'll have arctan of x over 2. So theta is replaced by arctan of x over 2. And then sine of theta needs to be replaced by something, so does cosine, and then we'll add our c. Sine of theta is opposite over hypotenuse from right triangle trig, right? So that's going to be the side opposite theta, which is x, divided by the hypotenuse, which is the square root of x squared plus 4. So we'll sub that in here, x over square root of x squared plus 4. And cosine is similar. Cosine, from remember, so ka toa. Cosine is adjacent over hypotenuse. The adjacent side is 2 when the hypotenuse is the square root of x squared plus 4. So we replace this cosine of theta with 2 over the square root of x squared plus 4. And that's our answer. It's just not simplified. So from here, we simplify. 4 goes into 2, or excuse me, 2 goes into 4 twice. And we end up with this 1/4 of the arctangent of x over 2 plus x over 2 times this. And that square root multiplied by itself is going to give us an x squared plus 4 there. The expression under the radical. Now we could simplify from here, or not simplify, differentiate from here and take the derivative of this and eventually show that the derivative of this simplifies to that integrand. I'm not going to do that in this video, but we could if we wanted to. But let's go over the trig substitution steps. It looks like an x squared plus a squared, or a squared plus x squared. So we're going to make the tangent substitution. Prepare to substitute. Identify a, define x, compute dx. Simplify that x squared plus a squared before we substitute. Then substitute and simplify. And then when you get here, if you don't know what to do for your integral, for your antiderivative of the trig functions, go to your trig integrals guidelines. That would remind you, in this case, that we need to use our power reducing formulas for that even power of cosine. Apply that power reducing formula so you can antidifferentiate. And then this is a tricky one. When you do the power reducing formulas, you always end up with these multiples of theta inside here. Now the multiples of theta are not going to be well described by this triangle, because we don't have sine of 2 theta over here. We get sine, cosine, tangent of theta from this triangle. So we have to use this double angle identity, replacing sine of 2 theta with 2 times sine of theta times cosine of theta allows us to get that answer in terms of theta here, so that our trig functions are evaluated in terms of theta rather than 2 theta. And then we draw the triangle, use the triangle to come up with sine of theta, cosine of theta, and arctangent in terms of x, and simplify. So that's our 4-step process. I hope that helps. Let me know if you have any questions.